because I noticed that the audience is quite diverse. So I'll tell you about two things that I could have talked about, but I will not talk about, in case people are interested and they want to discuss it. So one is very much about particle physics, which was to discuss what observables one can define in the standard model of particle physics to determine what is the global form of the gauge group. Okay, so that's one topic, but I thought this was too particle physics oriented, given that there are so many condensed matter physicists. The other one that I think could have been of interest also to condensed matter physicists is a basic question about gauge theories in 4 dimensions, which is try to classify all the 4-dimensional chiral gauge theories that are trivially gapped. Okay. But at the end, I decided that I'll talk about something else. And the reason is that it's kind of a very basic question about gauge theories and the correspondence of gauge theories with gravity. So I'll tell you a little bit this story. And this is some work in progress. So, and the title of the draft so far is the ADS CPT correspondence. So in this lecture, I will not assume that you're an expert on ADS-CFT or that you're a super expert in gauge theories, but so I will try to build things from the beginning. So I'll just tell you some very basic things about the ADS-CFT that we will need to introduce the problem. So the basic idea of ADS-CFT is that you have a certain conformal field theory in the dimensions that lives at the boundary of gravitational theory in 1 dimension higher, okay? And I'm not gonna spend time saying how wonderful this is because you've heard it many, many times. What I want to discuss is what is the basic observations. So I want to establish some very basic dictionary. By the way, you should stop me anytime for any question, please. So on the CFT side, and then we're going to have the gravity side. So what was kind of the step 0 that led Maldacena to make this wild conjecture is the observation that a conformal field theory has enhanced symmetry from Poincaré to the conformal algebra. And the conformal algebra in these space-time dimensions is SO2, D. And the basic observation is that conformal symmetry was realized in gravity on ADS D+1, which can be represented as a hyperboloid. So this is the hyperboloid that represents ADS space. These SO2, D symmetries are realized as asymptotic symmetries of gravity in asymptotically ADS D+1 dimensions. More colloquially are the isometries. They are represented as isometries of ADS D+1. Notice that up to some minus signs is essentially the same as the isometries of a sphere. Okay? So that was a very basic, that's kind of the first step, that this is not completely crazy, that they match in some sense the symmetries. The other one is that you want to establish a dictionary between operators in the conformal field theory. By the way, I'm not sure if I'm blocking the blackboard, but no? Okay. Okay, so here there's a whole bunch of operators. Some of them are familiar, some of them are less familiar. And as we understood more things about gauge theories and conformal field theories, and we discovered that these theories have more operators than we thought we knew, every time that this happened, this posed a big, kind of a serious challenge to the gravitational theory, because now all of a sudden you have to be able to construct some dual description of those operators. So let me just mention a few that may or may not make an appearance during the rest of the talk. Sorry, so you can have local operators. for example, the energy momentum tensor, but you can have many other ones. Then you can have defects, which will play an important role in this story. So you can have line defects. So these are operators that are, instead of being defined on a point in space-time, they're defined on a curve. And for example, this could be like a Wilson line or a 't Hooft line, etc. And then in more recent years, we understood that gauge theories, under their hood, they always had operators that somehow we didn't know they were there. And one class of them are called surface operators. So these are operators that exist essentially in all gauge theories, that instead of being supported on a point or on a curve, they're supported on a surface in space-time, okay? So the first thing you want to understand is, okay, for every object on one side, there better be an object on the other that corresponds to it. And actually, this story is quite rich and subtle and complicated and beautiful. And depending on the quantum numbers of the operator and also the dimension of the operator, this can be described, for example, so the energy momentum tensor can be described, for example, by a gravitational wave. So for example, if this is the boundary of ADS, and I insert the energy momentum tensor, this will produce some gravitational wave that will propagate inside ADS. If you have a defect, so this again is the boundary of ADS. That's where the CFT lives. ADS is downstairs. So here you're going to have some non-local operator, like a line defect, supported on a curve. And then this object has to be described by in some regime, by some brane that extends into the bulk and that represents the line operator. So they're described either by gravitational wave, branes of various types, and the details are very rich and interesting. Depending on the details of what defect you study, you have to consider a particular type of brane. And that's where kind of miraculously you always land on your feet. The string theory dual always has the right objects with the right equations of motion for the branes that to provide the source for the defects. And sometimes you can also even do something more spectacular, that you can replace these operators by a different geometry. So you're no longer in ADS space. You're in a geometry that's asymptotically ADS. So when you're very close to the boundary, you go back to ADS, because essentially you go back to the vacuum state. But as you move inside, you get a non-trivial geometry and a non-trivial topology that encodes the quantum numbers of these operators. Okay, so that's kind of the general story. Another part of the story that will be important is that if the conformal field theory here has a flavor symmetry, a flavor global symmetry, like for example, QCD has SU3 flavor, what does this correspond to in the bulk? This corresponds to gauge symmetry in ADS D+1. Concretely, this means that in ADS D+1, you have so you have a global symmetry, let's call it GF. There are GF gauge fields in ADS D+1. And more precisely, this statement means that when you have a gauge theory which has a boundary, the global symmetry of the boundary theory arises as an asymptotic gauge transformation that acts non-trivially at the boundary. So that's a key part of the dictionary also. Good. So now let me give you, so this is very general, let me give you more concrete details for the kind of the Ising model, or kind of the basic example of ADS CFT, which is the duality between 4-dimensional n equals 4 super Young mills with gauge group with Lie algebra SUN. If this was LaTeX, I would write math frac, but I don't know how to really draw it by hand. But this is dual to type 2B, string, forget about the name, some type of string theory in ADS 5 and CS5. Okay? Now, here already is an interesting thing. Usually, we know when we study gauge theories, we have to specify not only the Lie algebra, you have to specify the gauge group. So the choice of gauge group, so given a Lie algebra, there are many gauge groups that can be associated to it. For example, for SUN, you could have SUN Lie algebra, or you could have a gauge group, or you could have PSUN, which is SUN conjugated by the center, for example. And this data is encoded in a choice of boundary condition in ADS. Okay? That's something I could explain, but I'll leave it for now, like that. Here, just going here, the SO2,4 symmetry maps to the ADS5 isometries. Now I have to give you a little bit of details. We'll come back to that more later. What is n equals 4 superioring mills? This is a gauge theory that has the following content. It has a connection, a four-dimensional gauge field within 4 dimensions. It has 6 scalars. You will understand why where the number 6 comes from later. Then it has some fermions. They have chiral fermions, of both chiralities. Okay? They all transform in the adjoint of the gauge group. And what's important to mention here is that when you have a gauge theory and you have matter, usually there is like a flavor symmetry that acts on the quarks and the Higgs fields. And if you're careful about this, so this I index is a 6, is a vector representation of a spin 6, also known as SU4. And this A index is a spinor of SU4, of a spin 6. So this theory actually has a spin 6. This implies that this theory has a spin 6 global symmetry. So now the question is, how is this realized in ADS? 5 times S5? Well, so this SO6 corresponds to the isometries of the phi sphere. Equivalently, when you write down the effective field theory in gravity in ADS5, you get spin 6 gauge fields in ADS. So these are a very concrete example of this story I was telling you here. Okay? But now you see that the gauge fields have a beautiful geometrical origin, as in the Kaluza-Klein idea that an isometry of when you dimensionally reduce a gravitational theory from higher dimensions to lower dimensions, if the manifold that you reduce on has an isometry, they manifest themselves as gauge fields in the lower dimensional theory. Okay, now here is an interesting thing to tell you how. I was just going to mention this example to see how tightly neat the two theories are. So now you can look at this theory, and you notice that alpha alpha dot is the usual notation for a left chiral and a right chiral spinor. Then you notice that the SU4 symmetry is not chiral. They transform differently for the two chiralities of the spinors. So actually it means that the SU4 symmetry has a 't Hooft anomaly. Which means that if you couple your theory to background gauge fields for an SU4, spin 6, whatever, connection, you have a non-trivial triangle diagram that's proportional to, can someone tell me what is proportional to? So that I'm just not talking to myself. Essentially, you just have to count the number of fermions. So this is the SU4 quantum number. How many of these fermions there are? Well, is in the adjoint is the dimension of the gauge group. So it's proportional to n squared. And this is just the usual statement that if you have a chiral symmetry, you get I'm sure you've seen this before. I'm not. Where these are SU4 gauge fields. And this is proportional to n square. So now you could ask, how is this seen in gravity? I told you how we saw that there is a global symmetry, but how do I see that that in the gravitational theory that the boundary has a 't Hooft anomaly? Here the point is that the 5-dimensional gravity theory has, as I already said here, that it has spin 6 gauge fields. But the point is that there is a term in the 5-dimensional theory. This is actually Chern-Simons term. I'm using this curly A to denote the SO6 gauge fields. And now the point is that you reproduce this anomaly by now doing a gauge transformation of the 5-dimensional theory, gives you D of something, and this is precisely the anomaly localized at the boundary. This is the usual disenformalism, if you're familiar with that, at the boundary of ADS. So the gravitational theory also knows about the 't Hooft anomaly of the gauge theory. Yes? No, it has to do everything with the it's the same, it's the one and the same, yes. Yes. Calling it flavor, yeah, it's a flavor symmetry if you're not sophisticated. If you're more sophisticated, you would call it an R symmetry, because yeah. But it's definitely, it's what rotates the scalars and the fermions. So it's a flavor symmetry, yes. But there's no problem on a flavor symmetry having 't Hooft anomalies, right? There is no problem. Exactly, it's a good thing. 't Hooft anomalies are good things, not bad things. No. So by Neuhausen and friends constructed gauge supergravity in 5 dimensions for obscure reasons in the 80s. And if you look at the Lagrange and say, look, there is this term. And yeah, no, I didn't put anything by hand. That would be not nice. No, it's kind of a remarkable thing. The theory has that term, and it does exactly what it needs to do to reproduce the 't Hooft anomaly of the boundary field theory. Okay. Good. So all this is very nice. So why am I telling you all these things? So now, in particular, you could say, is there anything else I could say about symmetries of n equals 4 super meals, or for that matter, for any of the CFTs that appear? Yes. Okay. Usually, okay. So whenever you have a DSCFT, you may start in a theory in 10 dimensions. But whenever you want to compute anything in the boundary theory, what you have to do is a Kaluza-Klein reduction. You write down an effective field theory in D plus 1 dimensions with an infinite number of Kaluza-Klein modes. Every Kaluza-Klein mode, every field in the D plus 1 dimensional theory is dual to an operator in the boundary. When you Kaluza-Klein reduce, Kaluza-Klein told us that if you have a space with an isometry, it manifests itself as a gauge field in lower dimensions. So in ADCFT, whenever you do any computation of correlation functions, you always work in D plus 1 dimensions. No, the gravity theory is in 5 dimensions. No, the gravity theory is in 5 dimensions. No, come in. You know this. So the gravity theory is in 5 dimensions, the boundary theory is in 4 dimensions. And even though you started with the theory in 10 dimensions, to compute observables. Yes, as Kaluza-Klein told us, yes. Sorry? Yes, I believe so. Yes, I think so, yes. That's not how Neuhausen wrote it down, because you could just write down what is the gauge supergravity action, and it will appear there, but yeah, there's obviously a 10-dimensional origin, yeah. I mean, this n square has to do with fluxes and stuff, right? Yeah. If you know anything about ADSFT, this n square is essentially Newton's constant in Planck units. So it's the right normalization of the gravitational action. So what can I say? Can we say something more about that? So then this led me to think about the following question, that any relativistic quantum field theory has CPT symmetry. And of course, the conformal field theory is in particular a relativistic quantum field theory. The fact that this statement is true between friends intuitively is just a statement that a CPT transformation is an antilinear transformation, but is related to essentially a pi rotation, is the weak rotation of a pi rotation in a plane in the Euclidean space. So that's why you have a relativistic invariant theory, and your Hamiltonian is unbounded from below, so that you can weak rotate. Any theory that has relativistic symmetry will have a CPT symmetry. And it may have, or not. This is not guaranteed. This is guaranteed. What I'm going to say now is not guaranteed. It could have charge conjugation. I call it C. So this is a transformation that maps particles to antiparticles. It can have parity, which I will take to act by reflecting on one of the space-time coordinates. You can reflect on all the spatial coordinates if you want, but that's not a nice thing to do in odd dimensions. That would not be, that would be part of the connected part of the Lorentz group. So I'm going to pick this. And you could also potentially have time reversal that maps time, that inverts time, and is an antilinear operator. Okay? Good. So a couple of things I want to say about this. So the Lorentz group, so essentially the Lorentz group has 4 components. One of them, let's call it lambda, is connected to the identity. This is all we require quantum field theories to be invariant under. That's all we care about. No, that's not. I don't want to say that. This is all you require to prove structural theorems like the CPT theorem. Then you could have three components that are not connected to the identity, and essentially these are obtained by taking a piece of the connected component and multiplying by parity, time reversal, or PT. Okay? And the way you should think about P and T, PT are outer automorphisms of the Poincare algebra. And now you can sit down and think how, physically, if you get the signs right of how P and T should act on the Lorentz Poincare generators. Okay? Good. So now now you will understand the title of my talk. Now the question is n equals 4 Young-Mills, or for that matter, any of the holographic duals, gauge theories or conformal field theories, does it have a CPT symmetry? This is an extremely elementary question. For example, let me say n equals 4, to be concrete. Have C, P, or T? That's question number 1. And question number 2, what is the gravitational dual? Okay, so let me start this. Okay. So I'll do it like, this is something that you could do in a quantum field theory class, even though Marina doesn't believe me, but you will see. I will do it like, just to try to understand, how do you know whether the theory has these symmetries, okay? So let's start what is n equals 4 super Young-Mills. One very useful perspective, and you will see why, is that this is obtained as a dimensional reduction of 10-dimensional n equals 1 super Young-Mills. What is this theory? This theory is a theory of a connection. So it has the usual Young-Mills term, where m and n now run from 10 dimensions. And then you have a lambda is a Majorana-Weil spinor in 10 dimensions. And again, all fields are in the adjoint. And the way you get n equals 4 super n mills is by dimensionally reducing. What does this mean? It means that here you started with a theory that's 10-dimensional Minkowski space. What you do is you think of R19 as R1,3 times R6. And essentially, you take all your fields to be independent of these R6 coordinates, okay? And if you do that, you get the Lagrangian, and the field content splits nicely into a gauge field, 6 scalars, and the fermion. For the analysis today, it will be useful to keep the spinor indices of lambda to be 10-dimensional spinor indices, even though it's, of course, a 4-dimensional field. But that's not enough. That's one piece. Then you could have the theta angle, the topological term of gauge theories. You could add theta over 16 pi square trace f wedge f. Here's a question for the audience. Usually we say that in theory of massless fermions, the theta term can be rotated away. Why cannot it be rotated away in n equals 4 super mills? Okay, you could, we can discuss it later. And actually, that's not enough. Depending on the choice, if the gauge group is not simply connected, then you can have what's called discrete theta terms. These are terms that when you sum over your functional integral over gauge fields, G gauge fields, this way, depending on the topology of the gauge bundle that you're summing over, they will contribute phases to the partition function. Okay? I'm not going to go too much into the details of that, but that's an interesting observation that gauge theories have more parameters than perhaps you thought they had. Okay? So now let's do charge conjugation. So how do I know if the theory has charge conjugation? Let me start with pure Young-Mills. At some point, we'll have to accelerate, but not yet. So let's start with C. So I start with the Young-Mills action, and I want to ask the following thing. I'm doing a transformation that acts on the gauge field in this way, and I'm asking whether it leaves the Lagrangian of any F mu A, F mu A. A is the adjoint index of the Lie algebra. I want to ask, when does this transformation leave the Lagrangian invariant? So there are two constraints here. You have to remember that F mu is the curvature of the connection. It has a linear term, and it has a nonlinear term. Where this FABC is the usual structure constants of the Lie algebra. Now, for this transformation to be a symmetry of the Lagrangian, you need the nonlinear term to transform the same way as the linear term. Otherwise, you have no chance of success. And this gives you this nice condition, which is OAD, OBE, FCAB equals OCG, FGDE. G is demanding that this guy is homogeneous like this guy. That's condition number one. And now that I pulled out something homogeneous, it has to leave this guy invariant. But that's easy. It means that O is essentially an orthogonal transformation. Okay? So what's the physical meaning or the mathematical interpretation of these equations? This is a statement that in order to have a charge conjugation symmetry, you require that O is an orthogonal. This is the orthogonal part. Automorphism of the Lie algebra. This is precisely the definition of what an automorphism of the Lie algebra is. You take your generators, you rotate them, and you demand that the structure constant remain invariant. Okay? But now there are two possibilities. If O is an inner automorphism, C is not a symmetry. Can anyone tell me why this is not a symmetry? Essentially, if it's an inner automorphism, there are no operators in the theory that are charged under it. So you have nothing charged under it, it's not a symmetry. Every operator is invariant under it, so it's not a faithfully acting symmetry. So that means that you have C conjugation symmetry if O is an outer automorphism. Of the Lie algebra. So when does this happen? This only happens if the Lie algebra is SUN for n bigger than 2. The outer automorphisms of a Lie algebra have to do with the symmetries of the Dynkin diagram, believe me, for that statement. If the gauge group is SO2n or E6, okay? So any gauge theory, Yang-Mills theory with those gauge groups will have a charge conjugation symmetry. Sorry? Well, I'm not sure what you mean. If you have, you cannot call something a symmetry that doesn't act on anything. Then you could say that the standard model has monster symmetry. Yes? No, but do we agree that if you have you could only call a symmetry if it's a transformation that acts on something? If it doesn't act on anything, it's not a symmetry by definition. It's a symmetry if it acts on any operator. I don't care what operator, if it's made for fermions, if it's Wilson loops, if it's Tooth loops. Sorry? Theta cannot be. No, I mean the gauge field. The gauge field is always in the adjoint representation, right? Yeah, but then right then, by virtue of the fact that if it's an inner automorphism, then the statement is that any gauge invariant operator is automatically invariant under that transformation. So therefore, it's not acted on by this transformation. So it's not a symmetry. Yeah, so then it's not a symmetry. No, that's wrong. That's a wrong thing to think about. There are many theories that have no C, no P, no T, but have CPT. One of them is known as the standard model. Yes. No, that's what I'm saying. C is trivial. C is trivial means it's not a symmetry. It's the same thing. C being trivial is the same as not a. You understand? I will discuss it in a second. Yeah. But I'll have to accelerate a little bit. So actually, you could ask, what about fermions and scalars and all of that? So leave this as an exercise. Write the Lagrangian of a fermion now. This is true in any dimension, more or less. A charged fermion. So it's and the fermion is in a representation R of the gauge group. You can ask, when does C exist? Well, let's write the most general transformation that will give the kinetic term of C invariant. The fermion invariant. You make this transformation, U equals U psi, where U is a unitary matrix. Then, if you look now at the term that couples the gauge field to the fermion, you immediately conclude that this is a symmetry if and only if this is satisfied. Where TAR is the representation matrices of the fermion in representation R. What's the physical meaning of this statement? The physical meaning of this statement is that these OAB, TBR, are the generators of a representation in the conjugate representation. So whenever you have an outer automorphism has the property that it maps acts on representations. For example, for SUN, it maps the fundamental to the anti-fundamental. Okay? So you have charge conjugation symmetry, essentially, if the representation R is equivalent to sigma R. And for SUN, let's be concrete, for SUN, this would be if R is if R is not complex. I'm being very careful with my words. If R is not complex, okay? Now you could ask, okay, so given this, so for example, that means that for n equals 4 super mills, in which all fields are the adjoint, you have C symmetry. Sorry? Yes, but SU4, it was a global symmetry, not a gate symmetry, right? Yes, no, but yes, yeah, that's a correct statement, yes. But I'm saying that here what matters is the transformation of psi under SUN, and psi is in the adjoint of SUN, and the adjoint is always self-conjugate under any outer automorphism. So that means that n equals, I could do the same game for the scalars, so you would get the same condition. So n equals 4 Young-Mills has C symmetry if the Gates group is one of those, okay? It's semantics. I'm saying that. There is a case where the C symmetry is trivial and is not broken. Yes, but then I already object to you calling it a symmetry. No, if it doesn't act on anything, if it doesn't act on any of the local, on any of the gauge invariant observables. No, you can implement it, but it's a useless implementation. Yeah, okay, you can call it. I don't want to call the identity a symmetry. Right. Okay, so. For example, in the standard model, you look at the quantum numbers of the quarks and the leptons. You cannot even write down well, actually, no. You could write down, but you will simply not obey this relation. You can write it down, but you will simply not satisfy this condition. Given that you're asking this, so now let's go back. Can a chiral gauge theory have charge conjugation symmetry? Who thinks that it can? Who thinks it cannot? The answer is that surprisingly, despite what many textbooks say, the answer is yes, actually. A chiral gauge theory can have charge conjugation symmetry. Okay, so now, how does it act on the n equals 4 Young-Mills field? So let me combine, since all the fields are in the adjoint, it will be useful to, so I don't have to write so many things, to write this gamma as this vector of all the fields of n equals 4. So in n equals 4 for SUN gauge group, charge conjugation acts by taking the fields and taking the minus gamma transposed. Okay? That's how charge conjugation acts on the fields. And indeed, C2 is a symmetry of n equals 4 super Young-Mills. Okay? What about parity? So here I'll have to accelerate a little bit. So here, you at first glance, you encounter an obstruction. So let's talk about parity. Why? Because I said that n equals 4 Young-Mills starts its life in 10 dimensions. And it's very, very clear that a parity transformation acts on the gaugino. So imagine I do parity in the x3 coordinate. It acts with a gamma matrix like that. But why is this not a symmetry of 10-dimensional Young-Mills, super Young-Mills? Because that would change the parity of lambda. No, the chirality of lambda. And lambda is a Majorana-Weil spinor. The transform field is in the other representation, so it cannot be a symmetry. So then you could say, okay, well, n equals 4 Young-Mills is a dimensional reduction of 10-dimensional n equals 1 super Young-Mills, so it will not have a symmetry. But there is a way out. What you can do is define a transformation that preserves the chirality in 10 dimensions, so it has an odd number of reflections of coordinates, but has an odd number of reflections in R1, 3. So remember I said that I have R1, 9, and I split into R1, 3 times R6. What I can do is now take a proper a transformation in spin 1, 9, which is in the connected component. Between friends, it means that you reflect an even number of coordinates here. An even number of reflections is in the connected part, right? It has determinant 1. What I can do is do reflection here on X3. So from the point of view of the four-dimensional theory, it's a parity transformation. It's in the disconnected component. It has determinant -1. And I choose here an odd number of reflections. For example, I could take X4, 5, and 6 to be reflected, sorry. So while this looks like a connected component transformation of spin 1, 9, is actually a parity transformation from the point of view of n equals 4 superior Mills. Okay, so now to make it this precise, we can write down what the transformations are. That will be a symmetry of n equals 4. Let me write and I'll explain. And a lambda is now rotated by a matrix that preserves chirality. Okay, let me tell you a few things. So I split, because clearly I have to pick here, say, three directions to flip. I'm splitting the I index into A and A dot. So this is 6 equals 3 plus 3. That's what I have here. So 3 of the coordinates are reflected. The scalars have to do with the coordinates in the R6. So 3 are reflected, 3 are not reflected. This is the usual way in which parity acts on a gate field. And the claim is that this is a symmetry of n equals 4, and Px is just x0, x1, x2, minus x3, okay? Good. So even though there was no symmetry in 10 dimensions, I was able to construct a parity transformation by combining parity with an action on the SU4 symmetry, on the SU4 internal space. Sorry? Yes, you could, and that's the idea. Something that is not, the thing that's kind of interesting is that something that is not a parity transformation in higher dimensions can become a parity transformation in lower dimensions. So for example, yeah, you could do it for 4D n equals 2, that comes from 6D n equals 1. Even if the theory is chiral in 6D n equals 1, I can concoct a parity transformation by acting on the R2 dimensional reduced space. Yeah, so it's a very general trick that you could apply. What about time reversal? So I'm not maybe not going to write this, but again, you have the same problem. Time reversal will flip chirality of the 10-dimensional spinner. So this is not a symmetry, but again, I can combine it with transformation on the 6 scalars to make it a symmetry. And what you end up is a transformation T, which is antilinear. So one thing that is very important here is that it's an antilinear transformation. So when you check the invariance, you have to take that into account. And it has the property that, for example, and I'll pick, okay. And actually, you have two versions. You can either choose the time reversal symmetry to square to t squares to minus 1 to the f. That means that you can couple n equals 4 super Mills to what are called pin plus manifolds. So these are unoriented manifolds that have what's called a pin plus structure. Is a generalization of the notion of a spin structure when you have fermions. But actually, there's another transformation that t tilde squared that squares to 1. And then you can couple n equals 4 Mills to a pin minus manifold. So actually, you can study time reversal in n equals 4 Mills by coupling the theory to either pin plus manifold or a pin minus manifold. Doesn't matter. Okay. Oh, and I should say for parity and time reversal, you could ask, is this always a symmetry? Okay, that's an important point. So charge conjugation was a symmetry for any value of G square Yang-Mills and the theta parameters, continuous or discrete. Parity and time reversal, since they act, essentially they flip the imaginary parts of the action. They're only a symmetry for when the theta terms contribute to the functional integral plus or minus 1. If they have an imaginary phase, they cannot be a symmetry. Okay? So in particular, theta for SUN, theta has to be equal 0 or pi for SUN. While C requires no constraints on theta, P and T symmetry require constraints on theta. Otherwise, the F dual is not P or T invariant. Okay. So what are these things in the bulk? I don't know what I did with the eraser. So I'm just going to write it down. So there are many things I could say, but let me just now tell you. So now that we found the symmetry and equals for superior Mills, we still believe that duality should be true. So the question is, where the hell is CPT in string theory in ADS5 and Z5? So now I'll tell you. Before saying that, let me make a nice observation that if you don't care about the gravity, time is up, okay. Yeah, okay. If you only care about field theory, this will be hopefully an interesting statement. So N equals for superior Mills has an SL to Z duality symmetry. That acts, is a non-perturbative symmetry that in particular acts on the coupling constants on the coupling constant of the theory and also the theta angle. And now you could ask, what does S duality do to these symmetries? So here is one claim. The claim is that P under S duality maps to CP, and T under S duality maps to CT. While C is invariant under S duality. Okay? So the S duality transformations of N equals 4 Mills act non-trivially on the discrete symmetries of N equals 4. And that's it. There are no more symmetries in N equals 4. You're not going to find more symmetries than this in N equals 4. Sorry? Yes. Yeah. So it's an automorph. It's a duality groupoid. That's what I would call it. Yes. But I'm saying that C of one theory maps to CT of the other theory. Yeah. I'm glad that you're careful about this distinction because people are usually not. Yes. Okay. So now, what is this in string theory in ADS? And now this is a case in which you thought you could get away with in life just by knowing gravity in ADS and not knowing any string theory, you would run into serious trouble. Okay? Yes. Yes.
So that would be a way, like, basically you have different possibilities, no, depending on the topologies that you can include.
But what I'm saying, well, as you will see.
I will say another thing that may be more interesting for string theory, but I'm just saying that, in general, you could also work without the string theory for answering this question.
You would not be able to answer this question if you don't use symmetries of string theory.
Not duality with N equal to 4 super Mills.
Yeah, I mean, in some.
I'm just saying that in quantum gravity you can still answer this question by saying what kind of geometries with what kind of symmetry, space-time symmetries.
Maybe you can, maybe you cannot. You have to show me an example where you can. Yeah. Yeah. No, I'm saying that I actually have serious doubt that that can be done. Yeah. So let me tell you something very basic about symmetries, world-sheet symmetries, and that's why I say that you have to go beyond gravity. Yeah, world-sheet symmetries of string theory. So this will be like a 2-minute tutorial. So string theory is a 2-dimensional quantum field theory that lives on, that makes the tube as it propagates in space-time. And then it's a two-dimensional quantum field theory, and it has fields, bosonic and fermionic, that are left movers and right movers. You're familiar with this from two-dimensional conformal field theory. Okay? So now, type 2B string theory has two symmetries that will be important for us. One is orientation reversal. This is the statement that you flip left movers to right movers on the worldsheet. That's otherwise known as worldsheet parity, not to confuse it with space-time parity. And the other one is called -1 to the f left, which is left, okay, space-time fermion parity carried by the left movers. Okay? It turns out that actually these guys generate an interesting algebra by defining A to be omega -1 to the f left and B to be omega. You can prove that very simply from kind of Polchinski 101 that A to the fourth equals B squared equals 1 and that BA is A inverse. So actually these symmetries generate the dihedral group of 8 elements. So it's a dihedral group of the square. Okay? So now I'm just going to tell you what the answer is. To explain the answer, I probably don't have time. But the way I arrive at the answer is by, in particular, looking very carefully at how the various non-local operators of the gauge theory transform under CPT. I use in a very deep way the dictionary that has been established over the years about how a given non-local operator is described by a particular brane or particular geometry, and try to understand which transformation will implement the action on the dual gauge theory operator. So here's the answer. So C will correspond to omega -1 to the f left reflection on all. So you have a phi sphere that can be represented by embedding coordinates like this. So C corresponds in string theory to omega -1 to the left combined with the antipodal map on the phi sphere. Yes? It acts on branes, it acts on everything. Oh no, you know. But you know that omega -1 to the f left maps DC brane to DC brane, but a D5 brane to an anti-D5 brane. You know how it acts on the closed strings, and you know how it acts on the open strings. You know both. No. I know how it acts on the objects of string theory. You know how it acts on D-branes, on fundamental strings, etc., etc. On Kaluza-Klein modes, on everything. What are you confused about? I'm saying something very basic. Yeah, but now, since you know how to construct the spectrum of massless closed strings from the worldsheet, you know how this object acts on those fields, right? So for example, it maps the NS-NS2 form to minus NS-NS2 form. But then you also know how it acts on the branes. I don't know what you mean. These are branes. I mean, the D-brane couple, like a, let's take a Ramon-Ramon field. A Ramon-Ramon field, if it's odd under this object, it means that you started with a brane here, it will be mapped to an anti-brane. So you know how it acts on everything. Yeah. P maps to -1 to the f left times reflection on 4, 5, 6. So this 3 is part of the space-time coordinate. 4, 5, 6 are part of the antipodal map on the sphere. And T to omega R0 reflects time, and 7, 8, 9. Okay? Yes? No, that's crucial. Okay, that's a very good question. Very good question. Omega -1 to the left flips F5. So you would say, it's not even a symmetry of the background, but if I combine it with those R blah, 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 it is a symmetry of the background. No, it's very important that, so this statement is a symmetry, are symmetries of flat space. Now you have to make sure that in your background, those are symmetries of your background, but for that you may have to accompany these world sheet symmetries by some transformation so that it's actually a symmetry, so that F5 is invariant under it. Yeah. Okay, so I will not tell you how this is derived. Maybe I will just finish with one statement that I think it would be interesting, irrespectively if you don't care about any of this, is that in any quantum field theory, so this kind of thought leads to the following observation, that in any quantum field theory that has and there are many examples of this, some of interest in condensed matter, and they appear in all kinds of dualities, like particle-vortex duality, in all kinds of dualities of gauge theory and gravity. There exists a canonical codimension 2 defect that's defined in the following way. So codimension 2 means that it has a transverse to space, so the defect will be a point. This is a transverse space. And the way you define this defect is that you draw an imaginary branch cut away from the defect. And then what you say is that you quantize the theory in which your fields, as you go around the defect. So let's call this the z-plane. If I go around the z-plane, the field comes back up to the action of charge conjugation. Okay? This defines a canonical codimension 2 defect, which actually it has a lot of interesting and fun properties and relations to dualities. It links. I mean, it links. It's a thing. You cannot. Okay, it's like be in the plane. You have a point in the plane. Let's not waste time on this. You cannot. Yeah. Yeah. It's extended in all the directions. Yes. It's a point here, but it goes in all the other directions. Yeah. So, for example, from this quantity, you can define the analog of conformal dimension of local operators for this defect by looking at the operator product expansion of the energy momentum tensor with the surface operator. Let me call it O sigma. This defines a certain quantity H that has interesting properties that you can measure. And you can ask, how is this guy in dualities? And here again, you're against the ropes, because now all of a sudden I'm telling you, n equals 4 Mills has this crazy object, but I'm running out of things to provide the dual of. So here is the answer. So this defect is actually a chiral defect. This C defect in n equals 4 superior Mills has a beautiful description in terms of type 2B string theory. So again, the theory saved itself. It can be described as, I'm going to say words that may not be familiar with everyone, but at least I want to say them once, is an object in string theory, which are called D-branes, coupled to an identifiable plane that wrap an ADS3 times S5 submanifold in ADS5 times S5. And now, remarkably, by doing computations of this object in ADS5 times S5, you're able to reproduce many of the properties of the charge conjugation defect in n equals 4 Mills. I could say more things, but since I'm out of time, thank you. Yes? No, I never. Yes. Yeah, so this is a very interesting and confusing question. Yeah, so the question, which is a friendly, nasty question, is that there is a slogan out there that there are no global symmetries in quantum gravity. So what do I was very careful not to I think I was careful not, when I was talking string theory not to use the word global. I said symmetry, okay? So now the question is, but it's still an interesting question of whether this should be thought of as a global or a gauge symmetry. And this is very confusing in flat space. Why? Okay, why? Because as you know very well, if I gauge type 2b by omega, you get type 1. And I don't think in any obvious way you would say that type 2b is the same as type 1. So I believe there is a certain sense, subtle sense, analogous to the case of ADS-CFT, where you say that it is an asymptotic transformation that behaves like a global symmetry. I believe there is a way of thinking about omega and -1 to the left in a way that is actually gauge symmetry. But this is a very subtle question. Definitely here, I believe that in a suitable sense, they should be thought of as gauge symmetries. Gauge transformations, yes. And by the way, another interesting thing is that now you could ask, I have this symmetry here. I could gauge it. What do I have to do in the bulk to gauge that? Well, what you have to do is now, this is a Z2 symmetry. In the bulk, you have a Z2 gauge field. So in order to gauge C, you have to change the boundary conditions of the Z2 gauge field. And that will give you, instead of the theory with gauge group SUN, you get the theory with gauge group SUN semi-product Z2. But yes, no, this is we should discuss it. There is, people say these statements that it's a gauge symmetry, but especially for these two symmetries in flat space, this is very confusing because I don't think we would say, if you put a gun to your head, you would tell me that type 1 is the same as type 2b. Yeah. So it's a very good and important question. But I think there is a sense, asymptotic sense in which it can be interpreted as a gauge symmetry.